Okay, so now, we saw that an observable for a k-level system is a k by k Hermitian matrix, and the measurement is a measurement in the orthonormal basis of eigenvectors of A, right? And there are real eigenvalues which are the outcomes of the measurements. But now, in that sense, saying that we have an observable doesn't take us away from our notion of what a measurement was before, which was just pick an arbitrary orthonormal basis. But now we can ask the question, is this new notion of a Hermitian operator as general as our old notion? In other words, suppose that I pick an arbitrary orthonormal basis, phi1 through phi k, and I pick arbitrary real outcomes that I want, lambda 1 through lambda k. Can you design for me an observable A, meaning a Hermitian matrix, a k by k Hermitian matrix, which has exactly these eigenvectors, phi 1 through phi k, and eigenvalues lambda 1 through lambda k? And the answer is going to be yes. These two are completely equivalent. So let's see why. So let's actually do this first by an example. So suppose that we want our eigenvectors to be 1 over square root 2, 0 plus I over square root 2, 1, and 1 over square root 2, 0 minus I over square root 2, 1. And the eigenvalues are plus 1 and minus 1. Okay, so how do we design an operator A which has these eigenvectors and these eigenvalues? Okay, so let me remind you about something that we saw before, which is how do you create a projection matrix? So suppose you want to project a state onto the state phi. So you're given some state phi, and you want to project onto phi. There's a linear transformation that does this. There's a transformation P that will do this for you. So how do you design P? Well, we saw that there's a very nice way of designing P in this bra-ket notation. So it's just ket phi times bra phi. Okay, so this is the projection onto phi. This is the operator that does it for you. And the way you check this is if you now look at P times psi, what is it? It's phi, phi, psi. And what's this? Well, if you group these two together, so it's this way, right? So this is what you're actually doing, but now you use associativity, or in this bra-ket notation, you just look at it, and you look at it in a different way, and you just look at this piece, and that's the inner product of phi and psi. And so this is the inner product of phi and psi, and what you get is that multiple of phi. So this is, that's the coefficient, that's the complex number, and that's the vector. So what you've managed to do is project psi onto the vector phi. And okay, that's how long the projection is. So of course we'll see examples of this soon again, but let's see what we'd like. So I claim that what we can do is create the matrix A as the projection onto phi 1 with coefficient lambda 1 plus the projection onto phi 2 with coefficient minus 1. Now, why is this? Why would this be a matrix, a Hermitian matrix with eigenvectors phi 1 and phi 2 and eigenvalue plus 1 and minus 1? Well, let's actually go ahead and apply A times phi 1 Well, what do we get? It's phi 1 plus phi 2 times phi 1, which is phi 1. Oh, sorry, this is minus, right? Minus phi 2. Okay, but what's this inner product? Well, this is exactly 1. So you get phi 1 minus, what's this inner product? This is 0, because phi 1 and phi 2 are orthogonal. So you just get phi 1, right? And so here we are using the fact that these phi i's were orthogonal to each other, and so when you project, you'll actually project only onto phi 1 and not on any of the others. And so you pick up lambda 1 here. Okay, similarly, if you were to look at A times phi 2, you'd get minus phi 2, right? Because you had a minus here, and that's the only piece that would give you a non-zero contribution. Okay, so let's go ahead and figure out now what this really is in this case. Okay, so what's phi 1 bri phi 1, get phi 1 bri phi 1? It's 1 over square root 2 I over square root 2 times 1 over square root 2 minus I over square root 2, right? Conjugate. So what's this matrix? It's 1 over 2 minus I over 2 I over 2, and then that gives you minus I squared, which is 1/2. And similarly, phi 2 is similar thing. And if you work this out, you get, and so what's A? It's this minus this. And so if you subtract this minus this, you would get zeros on the diagonal, and you'd get I minus I. Okay, so now you could check that it has the correct eigenvectors and eigenvalues. So let's just check that A times phi 1, or let's check that A times phi 2 is minus phi 2. Okay, so let's check. 1 over square root 2 minus I over square root 2. And what do we get? Well, when we multiply, you get minus I squared, which is, sorry, you get plus I squared, which is minus 1 over square root 2. And then down here you get I over square root 2. And this is exactly minus 1 times 1 over square root 2 minus I over square root 2. So it's eigenvalue minus 1, as promised. So in general, I mean, this was completely general. So if you were given a set of orthonormal vectors and real numbers, and you want to create the corresponding observable, well, you just take the corresponding linear combination of the projectors onto these vectors. So you end up with a Hermitian matrix, and its eigenvectors are the phi i's and eigenvalues are lambda sub i's. Once again, to see this in one sentence, what you're saying is, well, phi sub j is an eigenvector because when you look at A times phi sub j, well, it's a sum of these projectors. It's, let's say, it's a summation lambda I, let me call this P sub I, projection onto psi sub I. But since psi sub j is orthogonal to each of the phi sub i's, its projection onto those is exactly 0. And so the only non-zero projection is the one onto phi sub j. And so you get lambda sub j times phi sub j. And so it's an eigenvector with eigenvalue exactly lambda sub j. And now, since each of these projectors is a Hermitian matrix, and the sum of Hermitian matrices is Hermitian, so we got the right observable. Okay, so what's the moral of all this? The moral is our two notions of measurement are completely equivalent. So you can specify a measurement either by specifying the orthonormal basis, or you can specify it by specifying an observable. And these two are completely equivalent.